So 2 pieces of advice. First, do lots of problems. The problems from today are pretty good, but they're not all of the things that you should look at. At a minimum, you should look at the problems from today, your quiz problems, and I'd say the last 2 exams. There's lots more, but I think that those are a small enough set that it's a reasonable amount. You can get through all of them. And not just look at them. Notice there's a word do. It's not look at lots of problems. Do lots of problems. You need to practice. The more you practice, the easier they get. The other piece of advice I have is take care of your health. We have people who take exams and they fall asleep because they stayed up the last 2 nights. It's a bold strategy, and it almost never pays off. So make sure you get plenty of sleep. Exercise if you need to exercise, eat healthy, and it pays off. And with that, we begin. So, nice warm-up. Find the integral of sine cubed y over cosine to the 5th y dy. Now with these problems, what we'll be doing is we're going to be looking for what technique should we be in, or what's our mindset. Now this particular problem, our mindset is pretty clear because we see trigonometric functions. When we see trigonometric functions, you think trigonometric integrals. Now the way that trigonometric integrals work is you say, all right, let me either use trig identities of various sorts to rewrite it, or maybe I can work with as it is, but ultimately we do things like make substitutions to turn trigonometric integrals into algebraic integrals. So the question becomes, how do we do this? And here's sort of one idea. Whenever you have odd powers of sine or cosine, that's a really good thing. So one thing we can do is we could say, well, let's pull off this odd power of sine. So I could write this as sine squared of y over cosine to the 5th y times sine of y dy. And the reason that this is good is if I pull off an odd power of sine, this sets us up for a really good substitution. Namely, if we were to make the substitution of cosine, then du would be negative sine. Meaning that this odd thing that we pull off, that puts us in a great place. The negative doesn't worry us too much. Now, before we can do that, of course, we have to write everything in terms of cosine. Sine squared, well, now is when we flex our trig identities. Sine squared is 1 minus cosine squared. And now we're really ready to go. So we say, all right, we've written things all in terms of cosine, and then we have that one sign off by itself, and that's right next to the dy. So we make our substitution. U equals cosine y. Du would become negative sine y. And so if we make that substitution, we will get 1 minus u squared over u to the 5th. And then a minus du. So the minus because of this minus sign. All right, well, that's not so bad. We can minus, so we can write it as u squared over u to the 5th, or if you like, u to the negative 3, and then minus 1 over u to the 5th, or u to the negative 5, du. So, all right, so from here, it's not so bad. You add 1 to the exponent, so u to the negative 2, divide, so negative 1/2. Here you get u to the negative 4. Divided would be negative 1/4. There's already a minus, so it's plus a 4th. And then we always remember if it's an indefinite integral plus c because we want all the points. That's our goal, all the points. And if we forget a plus c, that's a point. We don't want to lose that point. Now we're not done because we need to go back and start with what we had. So we started with y, so we have u equals cosine y. So we're going to have minus 1/2 cosine of y to the negative 2 and plus 1/4 cosine of y to negative 4 plus c. And that's good enough. There's things you could do, but there's nothing that really, from here, it's just fiddling around and simplifying. And oftentimes it's better not to fiddle around and simplify because mistakes have been known to happen. So, be careful. I have a lot of space left here. And so, there's a question. A query has arisen.
Why is it negative 2 power to the negative 2?
why did we get u to the negative 2? The rule for integration, you add 1 to the exponent. So we started with u to the negative 3. So we added 1. So there's enough space. We could do this problem a different way. And you're thinking, what? A different way? But it worked. Why do I need a different way? Well, we're in that fun stage of calculus where we have more than one method. So one of the things you could have done is you could have said, hey, if I think about this, what I have is I really have sine y over cosine y cubed times 1 over cosine y squared dy. And so what is that? Well, that's tangent cubed y times secant squared y dy. Now what can we do in this case? We can do tangent. So if we make a substitution, let's say v equals tangent of y, then dv is secant squared y dy. So this would become the integral of tangent to the, v to the 4th dv. Well, that's 1/5 v to the 5th plus c, meaning our final answer is 1/5. Why did I say to 4th? V cubed. I was anticipating. Be careful. Check your work. 1/4 tangent to the 4th plus c. And there we go. Now the question is, which one is the right answer? This expression here or that expression there? And they're both right. They're both right. If you work around with the trig identities, you'll see that they both work. And now you're thinking, well, could you do it a third way? Okay, interesting question. I always like a challenge. So you could actually do something a little bit strange, but I'll point this out just to, I'm not going to work it out all the way to the end, just to point out why we wouldn't do this. So notice I said, oh, we had an odd power of sine, but what else do we have an odd power of? We actually have an odd power of cosine. All right. Well, what could you do? Well, you could do the following. You could say, look, this is the same as sine cubed y over cosine to the 5th y times cosine y over cosine y dy. So that is sine cubed y. Downstairs it's cosine to the 6. I'm going to write that as cosine squared y cubed times cosine y dy. Now, previously we said, hey, this is going to become our du term. Well, we can do that again because now we can write everything in terms of sine. Because we have our sine cubed y. Then downstairs, cosine squared is 1 minus sine squared y cubed cosine y dy. So, doing a substitution, w equals sine of y, dw equals cosine y dy, then this would become the integral of w cubed over 1 minus w squared cubed dw. Now, I do not recommend this approach because you might notice it's getting pretty messy and you don't want to do that. Now, what's sort of the clue that we shouldn't do, or what's sort of the mantra? And here's the good rule of thumb. When you're doing integrals, you want to keep your numerator simple. And, just want to write this down. And you want to keep your denominators simpler. All right? That's our goal. When we're trying to simplify things, you always want to make things as nice as possible, and as much as possible, leave the downstairs as easy as you can possibly make it. Or if you can do something to make the denominator look simpler, do it. Just be very careful. Anytime you make your denominator more complex, you're going to make your life harder. And that's not our goal. That's not our goal. We want to make our life easier. That's why we take calculus. It's a nice, easy class. It's a nice, refreshing class to take at the end of the day. Number 2. Don't worry, we're not going to do like 5 variations on each problem. That one's just our warm-up, so we like to sort of explore different things. Most of them will be more straightforward. Find the integral of x squared over 4 plus x squared to the power 3/2. All right. Well, if we were thinking about the techniques, what's the right technique for this one? Trig substitution. Now what gives it away? Well, essentially that's square root. And you may say that's not a square root, that's a 3/2. But it is a square root. You know, it's a square root that's been cubed. And we have this, handy dandy guide for trig substitution. If we see square root of number squared minus function squared, well, then that says you're going to let u look like sine. If we see square root function squared minus number squared, well, that says u better be secant. But if they're both positive, in other words, we have an optimistic integral, then that should be tangent. In our case, we're both positive, so that's good. So we're going to let x equal, and be careful here, if this isn't 1, you've got to make sure you account for it. In this case, it's 4, which is really 2 squared. So x should be 2 tangent theta. dx, well, that'll be 2 secant squared theta d theta. And then, well, what will be the square root of 4 plus x squared? Well, it should be something nice. Because if it doesn't simplify, then we've made the wrong substitution. And if you work this out, what you discover is because of our trig identities, you get that this 1 plus tangent squared underneath, which is secant squared, and then you have a 4, so it simplifies to 2 secant theta. So, with that substitution, our integral becomes, upstairs, we're going to get 2 tangent squared theta. Downstairs, we're going to get 2 secant theta cubed. And the reason we're cubed is, remember, this is a square root. This is a 3/2, so we need to cube it. And then the dx becomes 2 secant squared theta d theta. So now we just sort of take a moment to sort of gather all our terms and see what we have. So what do we have? We have a bunch of 2's. We have a 2 and a 2, that's a 4. Downstairs we have a 2 cubed, so put them together we all get a 1/2. We have a secant cubed downstairs, we have a secant squared upstairs. So that would give us a secant downstairs, and so I'll write that as secant downstairs for right now, and then we'll work with it. So how can we work with this? Well, there's a couple things we can do. Now one thing we can do is we can say tangent squared has a nice relationship to secant. So we remember that tangent squared plus 1 is equal to secant squared. In fact, we used it implicitly over here, so I can replace tangent squared by the expression secant squared minus 1. And if we do that, well, we're going to get secant squared over secant, which is simply secant, and then 1 over secant, well, 1 over secant, that's the flip of secant, which is cosine. Now, we're in good shape, because we know the integral of secant. It's on our list of 10 integrals that we should know. So we know those 10. 1/2 log secant plus tangent, and we know the integral of cosine. The integral of cosine, positive sine, so minus 1/2 sine theta, and of course the plus c. Now we're not done because we got to go back all in terms of x. And to finish that, we say, well, let's come back to our substitution. Tangent of theta was equal to x over 2. And so we think of this as a triangle, and we mark our sides. So we have theta, tangent's opposite over adjacent. So Pythagorean theorem gives us 4 plus x squared, the square root of that, as hypotenuse. And of course, we should remember that we should expect this type of expression here because that was motivating our substitution. It should match. If it doesn't match, something's wrong. We should go back and check. All right, so we can read off our answer. Now, secant, well, secant is the hypotenuse over the adjacent, so the square root of 4 plus x squared over 2. Tangent is opposite over adjacent, so plus x over 2, and then minus 1/2. And sine, well, that's opposite over hypotenuse. So x over square root 4 plus x squared plus c. And that's a great answer. That's a great answer. Now, I will say, you might go and plug it into a calculator or maybe one of those online computation tools. And if you do, it's possible that the answer will look like the following. 1/2 log square root of 4 plus x squared plus x minus x over 2 square root 4 plus x squared plus c. Now, I don't know if you will, but it is possible that you will see that. Now, why do I say that? Just to warn you that sometimes things have different expressions, different ways to write equivalent forms. Now, do you see why these are actually equivalent answers? It's a little subtle, but fun to point out the subtlety. Yes?
I have a question. It's a little bit
Sure.
backwards.
Okay, all right.
Square the x squared on the top of the original integral, that's 2 tangent theta. You don't square the coefficient with it?
Oh my gosh, I got that wrong. I am so sorry. That should have been 4. You should point out my silly mistakes earlier. Steve, you silly person. You forgot a silly thing. Oh, I did? Yes, you did. Oh, that sounds about right. Okay, there we go. Caught up. All right. Thank you for pointing that out. So the reason these are the same is you can actually rewrite this. Notice that on the inside here, you'll get log of square root of 4 plus x squared. Can't write very well. Plus x all over 2. And properties of logs say you can write this as log of square root of 4 plus x squared plus x minus log 2. But log 2 is a constant value, and constants can be sucked up by constants. So that's why you might see a different expression as the answer. Now, in case you're wondering, would we accept both? And the answer is, of course we would accept both. We are after the correct answer, and we're not after simplify. You were probably told when you were in high school, when you get to college, they're going to expect you to simplify. Lies, all lies. That's not what is true. When you get to college, we expect you to get the right answer. That's what we're after. All right. Recall that the error in the trapezoid rule for f of x over the interval a less than or equal to x less than or equal to b is bounded above by this expression, m times b minus a cubed over 12n squared, where m is the max of f double prime of x for a less than or equal to x less than or equal to b. Now use this error estimate to bound the maximum error for the integral of f of x equals e to the 4x using the trapezoid rule for the interval -3 less than or equal to x less than or equal to 0 with 20 intervals, n equals 20. Now, in case you're getting nervous, do I need to memorize this formula, m times b minus a cubed over 12n squared? I want to be very explicit about this. You do not need to memorize the formula. If we ask you about this, we will give you the formula. Very rarely have we asked about it, but just be ready in case you do. And so I want you to focus on using the formula. So how do we use this formula? Well, we start identifying things. Some things are pretty easy. We can talk about a and b. So we go from -3 up to 0. So there's our a and our b. In this case, we have n, so that's great. And so we look at it and say, okay, we have n, we have b, we have a, we need m. So this is actually the hard part of the problem. So how do we get m? Well, we take a look at the second derivative between our endpoints. So we have our function f of x. We take our first derivative. That's 4e to the 4x. We take our second derivative. That would be 16e to the 4x. So there's our function. Now you might say, wait a second, this is bad because e to the 4x gets huge. It's huge. But remember, I don't have to look at e to the 4x over all numbers. I'm looking at e to the 4x for the interval between -3 and 0. And if I look at it that way, I say, oh, well, e to the 4x is going to be as large as possible. The max value will occur at 0. Because otherwise, I'm going to have e to a negative number, which is smaller than e to the 0, which is 1. So this m, which is going to be the max of 16e to the 4x, for negative 3 less than or equal to x less than or equal to 0 is going to be 16. So I can use choose m equals 16. So now our error, well, we can say our error, if you like the absolute value of the error, is less than or equal to, we plug in what we know. We know m, that's 16. b minus a, so 0 minus negative 3 cubed, and divided by 12 times 20 squared. And, well, you don't really have to simplify. Well, that's 16 times 3 cubed over 12 times 20 squared, and there's the answer. At least there's an answer. Now, this is not saying that the error is exactly this. This is sort of a bound for error. Oftentimes our error is much better, but mathematically this says it's definitely no worse than this. All right. Any questions about this one? Because this is a little bit different than some of the problems that are on old exams. Okay. All right. Number 4. Find the integral of 2 divided by z cubed times z minus 1. So, what technique should we be using for this problem? Partial fractions. Yeah, we're a little bit partial on this problem. Now, the giveaway is what type of thing you're doing. Now, in our case, we're doing a polynomial over polynomial. All right, so when you see polynomial or polynomial, you think partial fractions. First step is you check your powers, and you say, well, upstairs it's a constant. That means it's degree 0. Downstairs it's 4th degree. All right, so I don't need to do long division, but you should always check. Sometimes you may need to do long division. All right, so we figured out it was partial fractions. We checked for long divisions. Next thing, we make sure the denominator is factored. And, oh, that's very nice. They already did that for us. Well, that was good. They don't always do that. And so, really, we jump right into our partial fractions decomposition. So we have 2 over z cubed times z minus 1. We say, all right, well, what is that going to be? Well, I have this z cubed, which means I'm going to actually build up to it. I'm going to have a z term, a z squared term, and a z cubed term. Then I'm going to get a z minus 1 term. So there's going to be 4 different coefficients I have to find. Now, you can always check. There's a quick check to make sure at least you're on the right trail to see if you've set it up right. It's a 4th degree polynomial downstairs. There should be 4 numbers I have to solve for upstairs. So whatever the degree is downstairs, that's how many numbers you need to be solving for upstairs. And if they don't match, something's not set up correctly. So be careful. So we clear our denominators. So we'll get 2 is equal to a times z squared times z minus 1 plus b times z minus 1 plus c times z minus 1 plus d times z cubed. And at this stage, we start working with the equations. So, what are some things that we can do?
I have a question really quick.
Sure. If I made a mistake.
How you figure out what z is equal to, like a, b, c, d?
Well, how do I figure out?
How you choose what z terms to put with each of those, like a is z squared times z minus 1. Like, how do you figure
Okay.
out
So how did I go from the first line to the second line is your question.
Yes.
Okay, so let's say you believe me when I talk about the setup. So when I'm going from the first line to the second line, what's happening here is to say, look, I have to say it's a personal weakness of mine. Something I've struggled with for a long time is fractions. Fractions have they've stumped me for my whole life. And so I say, fractions, I don't want you in this problem. So the way I do it is I think about doing the following. I'm going to multiply both sides by the original denominator, z cubed times z minus 1. And when I do that, all the fractions go away. So now we see what's left. Well, when I multiply it by z, I'm going to get one z taken care of, so I'm still left with a z squared and a z minus 1. When I come to the z squared in the denominator, now there will be one z left and a z minus 1. Here, with the z cubed, all the z's are gone, but there's still a z minus 1. And with the last one, I got the z minus 1, but I still have the z cubed. So that's how I go from one line to the other line. Now, there's another question. Yes? No, you shouldn't apologize. You should be like, this is exciting. I want to know.
Why is b over z squared? Isn't this supposed to be like bz plus c?
Okay, so there's a question. Why is it b over z squared? Because oftentimes we have this setup with partial fractions. And so you have to think about the rule. So where can I put the rule? If we had something like in our denominator, say it was like z squared plus 1, because that's something that we would have to have like an az plus b. So there's that rule in place. But let's be careful about what's going on here. Now what you look at is you look at sort of like what's your base thing. So there's two possibilities. What you could have is what's called a irreducible quadratic. And that's the case where it's like, try as I might, I can't factor that quadratic any further without things getting complex. Whoa. That's complex roots. All right? So if I have something where I can't factor further, that's an irreducible quadratic. And in that case, I have to have the az plus b. Now the thing is, the z squared is not an irreducible quadratic. What it is, it's a linear term. So cz, this is the linear. That means I was able to factor all the way. But it's a linear to a power. So what you look at is you say, well, what's inside to the power? If it's what's inside is a linear term, you just need a one thing. If what's inside is an irreducible quadratic, I would need two. So that's what you go by. So that's a good question. It's not so obvious. I will say, by the way, if you're going through these problems and thinking, these are kind of tough problems, I will tell you, I sort of like went up a little bit in difficulty for the practice problems. Because I figure people prefer the practice to be more difficult than having the test be more difficult. At least that's what past surveys have indicated. So I am not claiming you're going to see like having to solve 4 things on the exam. So I'm not claiming that you won't. I'm just saying we're probably going to be nicer to you. All right. So continuing on. So once you get down to this stage, I like to say, choose wisely. A good choice will get you closer to an answer. A bad choice will get you further from it. What's a good choice? 1 is a wonderful choice. So I could choose z equal 1, because 1 has beautiful things. It says that 2, well, the a term drops out because there's going to be a 1 minus 1. Similarly, the b and the c. Then you get d times 1 cubed. So we've already solved for one of our 4 variables, d equals 2. Is there another good choice? 0 is a great choice, because there's lots of z's. The a term will go away, the b term will go away, because you got that z. The d term goes away this time. And now we get c times negative 1, which tells us that c equals negative 2. Now, at this point, we say, we're running out of good terms. But that's okay, because there's actually 2 ways to do things. There's actually many ways to do things, but there's 2 big ways, and we'll do a combination here. So choose good values. That helps you get some of the terms. And if you get stuck, and that's and you say, well, what can I do to get the rest? There's a sort of your path bifurcates. You could pick some random values and set up some equations. Or the other thing you do is look at coefficients. So let's look at coefficients. Come over to the left-hand side. And this will sound like a trick question, but I assure you this is a serious question. What's the coefficient of z cubed?
0.
Okay, good. You saw that. So 0, which is the coefficient of z cubed. Now we come over here and we look for all the z cubes. There is a z cubed here, because if you expanded z squared times z, that would be a z cubed, so we get an a. If we came here, well, nothing will get z cubed. Similarly, for the next term than for the last term. So 0 is equal to a plus d. Well, we already know what d is. That's 2. So 0 equals a plus 2. So that helps us conclude that a is negative 2. Now let's go to the square terms. Okay, what's the coefficient of z squared on the left-hand side? 0, because there is no z squared. So if there's no z squared, it's like I have 0 z squared. Similarly, we have like 0 z cubed. That's why we said there was 0. Okay, let's come over to the right-hand side. Is there a z squared in the first term? Yeah. So we get 0 from the left, and that would be negative a. is the coefficient of z squared. How about from the second term? Yeah. It's b. bz squared. From the third term? No. From the last term? No. So 0 equals negative a plus b, which tells us that b had better be equal to a, but we already know that a should be negative 2. And now we've gotten all our a, b, c's, and d's. So now we're ready to go back to our integral problem. So, using our partial fractions, we can get that 2 over z cubed times z minus 1 dz is equal to a over z, so that's minus 2 over z, plus b over z squared, minus 2 over z squared, plus c over z cubed, which is minus 2 over z cubed, plus d, which is plus 2 over z minus 1. And if we're going to integrate this, it might be easier to rewrite it. So you have minus 2 over z, minus 2z to the negative 2, minus 2z to the negative 3, plus 2 over z minus 1. And we're ready to read off our answer. The integral of negative 2 over z, do you know that one? Negative 2 log z. Integral of negative 2z to the negative 2? Well, you'd add 1 to the exponent, so it would become negative 1. And then you divide by negative 1, so it becomes plus 2z to negative 1. Negative 2z to negative 3, you'd add 1 to the exponent, giving you negative 2. Divide by negative 2, so you end up with a plus z to negative 2, and then plus 2 natural log z minus 1. Plus c, and we're done. That's our answer. Nice. All right, how are we doing on time? We're doing fine on time. In fact, we've been averaging less than 10 minutes per problem. We're going slow. You're young. You can think better. You know, the brain slows down a little bit. Okay, I can already tell that there's a typo on this one, so I'm going to fix my typo. Look away while I cry over my mistake. Okay, find theta, sine theta, quantity squared, d theta. All right. Interesting. Well, how can we approach this? Now, if it was just theta sine theta, that wouldn't be so bad. What would we do? You do it by parts. Yeah, there's no big surprise. But now we squared it. So maybe we have to think a little bit differently here. So one thing we can do is we can certainly square each part. And we think, okay, theta squared, sine squared theta, d theta. Now we're like, okay, if I saw like theta squared times sine, I'd be happy. But I have that sine squared. So we'd want to try to think about it. And this is a case of saying, okay, is there a better way to write this? Can we do anything to help us rewrite this expression?
Could you rewrite sine squared as 1 minus cosine squared?
Well, you could rewrite sine squared as 1 minus cosine squared, but then you'd get sort of stuck in a loop. It's like, okay, now we got theta squared cosine squared. Aha! Let's write cosine squared as 1 minus sine squared. And it's like, wait a second, that's where we were.
Or you rewrite it as 1 minus cosine 2 theta over 2.
Ah, nice. Okay, so that doesn't get us in a loop. So if you see a sine squared and say, you know, I like the sine well enough, it's okay. I used to sing the song, I saw the sine. So, but the problem is the square. So we have these identities, and it's good to know. I say there's 6 identities which are going to get you all the way through calculus. And 2 of them are power reduction. So the one we need is sine squared. We won't need it for this problem, but I'm just going to write down the mate. Cosine squared is 1 plus cosine 2 theta over 2. So these are 2 of your 6 identities that you should know by heart, because they're very useful. And not just always in problems involving trigonometry, they can be helpful for helping you rewrite things to make things simpler. So in this case, if we apply our nice power reduction rule, well, we get theta squared, and then we're going to get 1 minus cosine 2 theta over 2 d theta. which we can really break up into two integrals. So we have 1/2 theta squared, and then we have minus the integral 1/2 theta squared cosine 2 theta d theta. Now, for the first integral, 1/2 theta squared d theta, I think you'll believe me when I can tell you that the answer is 1/6 theta cubed. Cool. That's a pretty straightforward integral, no surprise. For the second integral, where we have a theta squared cosine of 2 theta, what do we start to do, or how do we start? Do it by parts. Now, when you do by parts, there's sort of two natural parts. The 1/2 theta squared, the cosine 2 theta. We have to think, okay, which one is u, which one is dv? I claim that this is a case when we actually know for sure which one is u and which one is dv. Which one is u? The theta squared part. The reason why that should be u is because if you have polynomial, if you keep making that your u part and you just keep going, eventually it disappears. Because after enough derivatives, it goes away. So this will become our u, and this will become our dv. And so you have to do a little bit of work here. So let's see, du would be, bring that theta squared, derivative of theta squared, well, derivative of 1/2 theta squared, would be theta. Oh, that's nice. Cool. And what's the antiderivative of cosine 2 theta? So it's the antiderivative of cosine is sine, and then you have to make sure you get the 1/2. Okay, so minus, and I'm always paranoid. So I like to make sure I put parentheses here, because whenever I see a minus sign, I have more than once forgotten to put subtraction. So I want to make sure I put a parenthesis there. uv, so 1/2 times 1/2, that's 1/4 theta squared sine of 2 theta. Then minus the integral v du. So that'll become 1/2, and I'm just going to sort of move the terms around ever so slightly. 1/2 theta sine of 2 theta d theta. All right, so we're up to 1/6 theta cubed minus 1/4 theta squared sine of 2 theta. And this last part, what do we do for there? Do it again. Yeah, look, sometimes you get to do integration by parts multiple times. You should be like, cool, it worked really well once. It can work really well again. But usually whenever you do integration by parts multiple times, you always have to be consistent. If you're like, I'm changing my mind, I'm going to switch the role of what I call u and what I call dv. No, you're making your life terrible. You're going to get into a cycle. Break the cycle. Always be consistent. And so if you do that, life will work out. So in this case, du, that'll be 1/2 d theta, and the integral of sine, well, that's negative cosine, but because there's a 2 on the inside, negative 1/2 cosine 2 theta. Okay, so being careful here, so we had a minus, so we're at a plus this integral, so plus, and so I don't need a parenthesis if it's a plus. All right, then it's going to be uv, so 1/2 times negative 1/2 will actually make it minus 1/4 theta cosine 2 theta, and then minus the integral of v du. So we're going to get minus 1/4 cosine 2 theta d theta. So we're almost there. 1/6 theta cubed minus 1/4 theta squared sine of 2 theta minus 1/4 theta cosine of 2 theta. And then we just have to keep track of our signs. So the integral of cosine is positive sine. So we have minus, so that's going to be a plus. We had a 1/4. When we integrate cosine 2 theta, we're going to have another 1/2, so giving us 1/8. And then we'll get sine of 2 theta, and because we want all the points, a plus c. And we're good. So this one was integration by parts twice, and we're okay. There are some times where you have to do things where you do integration by parts twice, and you're like, oh, let me rearrange terms, and then it works out very nice. But all right. So let's try another problem. Number 6. Find the integral of arctangent 1 over y dy. Okay. So in this case, what do we do? What's the right technique? Well, it's not a cosine over sine, so be careful. It's arctangent, it's the inverse tangent function, which is, in my opinion, one of the best functions we have. Lots of great things can be done with arctangent. Really lots of wonderful things. There's a suggestion. Integration by parts. Ooh, what's sort of the clue? It's integration by parts. Okay, so the clue it's integration by parts is, I don't know how to integrate that. That's a great clue. But it's also because it has a nice derivative. So there's sort of a good rule of thumb. If you have an integral which has arctangent involved or has log involved, if you see one of those two things inside of there, think parts. Now, it's not going to be 100% of the time that it's parts. There might be some nice substitution. You should always be checking substitutions first before you start doing fancier things. But when you have arctangent and log, what happens is that you have something where the derivative becomes something that's a rational function. So like the derivative of log is like 1 over x. The derivative of arctangent is 1 over 1 plus x squared. So when you have that type of phenomenon happening, then that becomes a really good argument for saying, okay, we should do integration by parts. So the thing is, the reason why it's not always the most obvious is we say, well, where's the second part? And the answer is, well, just simply the dy is the second part. So if you make this substitution, the derivative of arctangent 1 over y, well, that would be 1 over 1 plus 1 over y squared. Do we need anything else? Well, is there anything else? And you're probably like, you left a big gap there. I bet you there's something else. Yeah, you gotta have to do make sure you follow your substitution all the way down. So, if you need to apply the chain rule, you apply the chain rule. And then, of course, v would be y. Now, you can actually, if you think about it, clean up the du, because this would become -1 on the top. Then you'd have, think about multiplying the y squared in. You get y squared times 1, which is y squared, and 1 over y quantity squared times y squared becomes 1. So that du is actually kind of looking pretty good now. So what do we have? Well, we have uv, so y, arctangent 1 over y, minus the integral of v du. So minus y over y squared plus 1 dy. Now, minus makes that a plus. And looking at this is probably an integral we can finish off in our head. How do we integrate y over y squared plus 1? And even if we can do it in our head, we'll make some notes on the side. Y over y squared plus 1? Should we do partial fractions on this? You could do partial fractions, but what you're going to get is you're going to get back to y over y squared plus 1. It's already been partial fractionalized. What do we do? Yeah, it's a substitution. The old ways are still the best ways. Substitution should always be one of the first things you check. You should always look for, is there a nice algebra thing I can do, a nice trigonometry thing I can do, or a nice substitution I can make? You should always look for those things first. And then we go and do all our Calc 2 good stuff. So if we set u equal y squared plus 1, then we'll see that du would be 2y dy. And we say, well, we have a y dy, so we're just off by a half. So that means we can do something like multiply by 2 and then multiply by half. So we're going to end up with plus 1/2 the integral of 1 over u is log of u, which is log of y squared plus 1. And for all the points, tack on a plus c. All right.
Question.
Yes, there's a question. Yes.
So for du, how do you go from arctan of 1 over y to 1 over 1 plus 1 over y squared?
So from this step to this step,
From the first step to the second step, du.
wait,
So like,
from where to where?
we have du is equal to.
The u, yes.
How do you get that?
How do I get that?
Yeah.
Well, the derivative of arctangent is the derivative of that, so it's just 1 over 1 plus whatever's on the inside squared. So in our case, it's 1 over y, that's on the inside squared. And then the chain rule says multiply that by the derivative of the inside. So now you multiply by the derivative of 1 over y. So it's y to the negative 1. So the negative 1 comes down. That's the minus sign. Y to the negative 2, because you subtract 1. And that's where the 1 over y squared is. And then if you kept going, it's a times the derivative of y, which is dy. So it's the chain rule. Sure. All right. Good. I think we're picking up speed. We'll finish with plenty of time. Plenty of time. All right. Evaluate the integral from 0 to 2 of x squared over square root of 4 minus x squared. Well, this sounds familiar. What technique should we be using? Trig substitution. Now, what can we do with trig substitution? Well, we have the little chart. I won't repeat it again. This is what kind of trig substitution is this? Is this? It's a sine kind, exactly. So this is x equals 2 sine theta. Now, dx would be 2 cosine theta d theta. The square root of 4 minus x squared, if you just work this out, this will become 2 cosine theta. All right, so we get to there. Now, this is an interesting case. There are sort of two branches. So let's do both. Let's do both. Okay. So notice that this integral, it's a definite integral. So if we're going to do substitution, what we need to do is work out what the integral becomes. So x squared. See, this time I'm going to remember, because I'm so paranoid, I made one mistake, I'm going to go out of my way to make sure I don't forget to square the 2. Downstairs would become 2 cosine theta. And of course, in my zealousness, I'm going to make other mistakes, but that's all right. Now, is what I've written down true? The bounds, right. This is a definite integral. And so if I claim this is equal, I better update the bounds. If you write a definite integral equals an indefinite integral, that's actually a false statement, which means you lose a point. And remember, we want all the points. So be careful. If you write and say this is equal to that, they better be equal. And if they're not, don't put the equal sign. Okay, so we've got to update the bounds. So remember, these bounds are x bounds. So x equals 0 to x equals 2. So if we say, all right, well, suppose we have x equals 0. We ask ourselves the question, well, when is it true that 0 equals 2 sine of theta? What angle gives it that? In other words, when does sine of theta equal 0? At 0. So that would say our new bound is 0. But again, I emphasize, this is a different type of bound because this is a theta bound. Now we plug in x equals 2. When does 2 equal 2 sine of theta? Sine of theta has to be 1. What angle does that? Pi over 2, pi halves. Okay, so making this substitution, we get the following. Now, nice things happen. The 2 cosine thetas cancel, and this becomes the integral of 4 sine squared theta d theta. Well, how do you integrate 4 sine squared theta? Power reduction. Right. So sine squared, that is going to be 4 times 1/2 minus 1/2 cosine 2 theta d theta. So this becomes the integral 0 to pi halves of 2 minus 2 cosine 2 theta d theta, which we could say, well, that's 2 theta minus, and the antiderivative of 2 cosine 2 theta, well, it would be 2 sine of 2 theta, then divided by 2, so the 2's actually end up canceling. And we're going to go from 0 to pi halves, which would give us the final answer of, well, 2 times pi halves would be pi. Sine of pi, which is, sine of pi is what? It's 0, yeah. Then plug in 0. 2 times 0 is 0. Sine of 0, 0. Oh, so everything else is 0. So this problem is easy as pi. Now, do you notice anything interesting about this problem that we've overlooked? And this will make, the question I'm asking is going to make a lot more sense after Monday. What happens to this function if you were to graph it? Well, at x equals 0, you can plug it in at 0. What happens at 2? Well, plug in 2. Upstairs you get 4, downstairs you get 0. So what's happening is it's blowing up. So that there's this sort of asymptote here. So this is what's called an improper integral, meaning it's an integral which involves infinity. Now you might say, well, wait a second, what happened to that infinity? How did it disappear? The answer is, it disappeared here, where these 2 cosine thetas canceled. Essentially what was happening was that cosine theta, that was your division by 0, but that dx happened to also be the cosine theta, and you got cancellation. So sometimes it's the case when you have these improper integrals that if you're careful with your substitution, you update your bounds, anything improper takes care of itself. Now, if you're paranoid about that, what you do is you write this in terms of limits. But this is one where I feel we can probably avoid that. So let's do one where maybe we're not so sure we can do that. So this is a different kind of what's called an improper integral, in that now there's an infinity upstairs. All right. So we're going to work around with this one for a few minutes. So here, we'll do this one in let's do this in a slightly different way, just to give ourselves something to try. So one way to do a definite integral is to start by saying, let's work with the indefinite integral. So I'm going to do the indefinite integral. And as I'm doing this, I can't help but notice I have a log of x squared plus 1 quantity squared. Can I do anything to write that in a simpler way? And you should always be suspicious when I ask questions like this. The answer is this 2 is inside that log as an exponent. So those can come down. So I can write this as x squared times 2 natural log x squared plus 1. All right. So what technique should we be using on this problem? Someone has said integration by parts. What's the giveaway? The natural log. If you see a log, you should think integration by parts. Now you might say, well, let me double check if there's a nice substitution. Like, for example, if I set u equal log of x squared plus 1, well, if the denominator had been like an x squared plus 1, it probably would have been okay, but it wasn't. So there's not a clean substitution. So yeah, we should be thinking parts. All right, so let's rewrite this, sort of setting us up for parts. And when we're thinking a log for parts, we're thinking of saying that log, that's going to become the u. So then everything else, well, that'll become our dv. All right, so what's the derivative of log of x squared plus 1? 2x over x squared plus 1 dx. So it's always 1 over the inside. That's the 1 over x squared plus 1. Then the derivative of the inside is what's on the top. What's the integral of 2 over x squared? Negative 2 over x. So we'll get uv, so minus 2 natural log x squared plus 1 over x. And then we're going to have minus the integral of v du. So there's already a minus in that v, so minus minus will make it plus. And then what happens? Well, we're going to have 2 times x times 2. So that'll be a 4. I can pull that out. The x and the 1 over x actually cancel, and we end up with 1 over x squared plus 1. All right. Well, do we know how to integrate 1 over x squared plus 1? Yeah, it's arctangent. So this becomes minus 2 natural log x squared plus 1 over x plus 4 arctangent of x and plus c. Because right now we're doing the indefinite integral. So now let's get to the definite integral. So the way we handle things like bounds at infinity is we do it in the following. We use a limit. We can say, well, this is 1 to infinity, natural log of x squared plus 1 squared over x squared dx is the limit as the top goes towards infinity of natural log of x squared plus 1 squared, integral 1 to b, over x squared dx. But now I say, look, I know I did the antiderivative, so this is the limit as b goes towards infinity of, and we work out what we have. So it would be minus 2 natural log b squared plus 1 over b plus 4 arctangent of b. So this is, you evaluate the antiderivative at the top bound, then you subtract. Now you evaluate it at the lower bound. Lower bound here is 1. So minus 2 natural log of 2 over 1 plus 4 arctangent of 1. Okay. I should have put in one more step in the middle, which is you take the antiderivative and evaluate from 1 to b. But this is what you'll get. Now we just start saying, okay, what's going to happen here? And, what does happen here? A couple things are pretty easy. First off, let's think of this as being broken up. So let's have this first part. Limit as b goes to infinity, negative 2 log of b squared plus 1 over b. We'll deal with that in a second. What happens to your arctangent? So what happens to arctangent as the inside goes off towards infinity? What does arctangent do? Goes to pi over 2. We have an arctangent lover in the room today. Well, we have at least 2. Yeah, so if you think about arctangent, it has this shape to it. And the horizontal asymptotes for arctangent comes from the vertical asymptotes for tangent. So as you head off towards infinity, this for arctangent arctangent itself goes to pi over 2, so this whole expression goes to 4 times pi over 2. So there's going to be a plus 2 pi. So that's coming from there. This part, there's no b in it, so it's just what it is. Minus minus makes a plus, so you have plus 2 natural log of 2. What about arctangent of 1? What's pi over 4? Good. And 4 times pi over 4 would just leave us with pi. And the minus, we don't forget to put the minus in, minus pi. So we have to figure out this limit. Now, if you plug in as b goes to infinity, the bottom gets huge and the top gets huge. So it's essentially like an infinity over infinity. So if you have infinity over infinity, what do? Yeah, you channel your inner le hôpital. Oh, le hôpital, mon ami, it's been too long. Yes. So we do le hôpital, and we say, okay, so this is the limit as b goes to infinity. Take the derivative of the top, so that would be minus 2 times, and then it would be b squared plus 1 times 2b, and downstairs it would be 1. So this is a limit as b goes to infinity of minus 4b over b squared plus 1. And now that you have it as polynomial over polynomial, you just look at the degrees. And you'd say, well, it's the first degree on the top, it's the second degree on the bottom, so what's the limit going to be? Limit will be 0, because it'll get small. The bottom grows faster than the numerator. So the limit that we were left with went to 0. We had a 2 pi plus 2 log 2, and then a minus pi. Put it all together, you end up with a full pi plus 2 log 2. And that's the answer. Okay. Find the integral of cosine of t over the square root of 3 plus cosine squared of t dt. All right. This one's going to be fun. I can just feel it. There's like energy in the room when I see this problem. It's like, whoa, this one's going to be fun. Oh. Okay, so let's think about what we can do here. So one of the things that oftentimes you look for is you say, do I have like a really good derivative floating around so that there's a suggested substitution? And this is one of those times. You see that cosine t dt? That says, hey, you know, there's a pretty good substitution you can make. So if we wanted to end up with our du part being the cosine t dt, what should be a good substitution? Would be sine. So the fact that you see this cosine t dt is sort of saying, hey, you should try to think about making things so that you get a sine involved. So we're going to look for sines. Say, well, we have this cosine squared. Can we do anything to make that look like a sine? Yeah, we can say cosine squared is 1 minus sine squared. So this will become the integral of cosine of t over square root 4 minus sine squared of t dt. Well, remember, cosine squared is 1 minus sine squared. So, all right. Now we're like, hey, that's what we had going for us. U equals sine of t. Du would be cosine of t dt. Life is great. So we get du over square root of 4 minus u squared. Now, we say, aha. What do we do next? Trig substitution. Now you might be saying, whoa, there can't be a trig substitution because I started with trig. But here's the thing. Don't worry about where you came from. Always worry with the problem that you have right now. So if you just saw that, you wouldn't hesitate trig substitution. So don't worry about the history. Worry about what do you have right now. Okay, so trig substitution says what should be our substitution? Sine. Well, not quite sine. What should it be? 2 sine. So 2 sine theta. All right. What would du become? 2 cosine theta d theta. All right. So this will become, we should also say the square root of 4 minus u squared. If you work that out, what will that become? Become 2 cosine theta. It's set up so that it cleans up very nicely. That's why we choose trig substitution. So we get the du, well, that's 2 cosine theta d theta, over the square root of 4 minus u squared, which becomes 2 cosine theta. Well, hey, this is a surprisingly nice integral. We should have put this one on the test. It becomes the integral of just 1, and therefore the integral is theta, plus, of course, the c. Now, are we done? No, we get to work our way back. All right, so what is theta? Well, sine of theta was u over 2. So now I don't have to do any triangle, because I just need theta. So forget theta, I'd say that theta is the arc sine of u over 2. So, updating, we now have our answer as arc sine of u over 2 plus c. Are we done? No, because what do we need? We got to go back to t, because we started in t, so we have to end in t. So we say, okay, but what is u? The answer is that u is sine of t. And there we go. So the integral of cosine of t over the square root of 3 plus cosine squared of t is arc sine of sine of t over 2 plus c. All right.
can't cancel the x and the sign?
No, because of the over 2. See, if there were no 2, it would just be t. But that would be suspiciously too nice. Now, mind you, your instructors like you, but not that much. So yeah, you got to be careful. Yeah, arcsine and sine would cancel, but because of the 2, they don't. They do not, unfortunately. All right. Number 10. We're in the double digits now. Evaluate the integral from negative infinity to positive infinity of 2 over e to the x plus e to the negative x dx. Well, this is an integral which involves infinities. Before we do that, let's just sort of see if we can figure out what to do. So suppose you're asked to find the integral of 2 over e to the x plus e to the negative x dx. Yes?
I think you mentioned that we're going to cover this on Monday. Does that mean that because we're doing it now that they're also going to be on the exam on Thursday?
Yeah. Isn't that great? You know, it's going to be fresh. You know, now it's not like that stale. It's like, man, you know, trig integrations. I did that so long ago. Like, oh my gosh, who remembers those? But indefinite integrals, wow, I know how to think about those. Now, we do also know that we've just covered it. And so there was a deliberate attempt to make sure that any problem that we wrote would take into account the rather short length of time. So, but you're going to discover that indefinite integrals are really just saying, yeah, what happens as b goes to infinity or a goes to negative infinity. They're not actually too bad. They're going to leave you with a warm, fuzzy feeling if you do them well. Okay, so 2 divided by e to the x plus e to the negative x. It's not so clear what to do. So we think about it for a while. We meditate and we say, well, what's another way to write it? One of the things is e to the x and e to the negative x are not really the same thing. It would be nice if they were sort of more compatible. So we start thinking, is there another way to write that? So what about e to the negative x? How can you write that? 1 over e to the x, right? I mean, and this may or not help us, but if we don't have a better idea, let's at least stare at it. So we say, okay, so certainly the following is true. It's 2 over e to the x plus 1 over e to the x dx. And then we say, all right, a fraction inside a fraction? No, that's not good. We don't want that. We don't like fractions within fractions. We just want to deal with a single fraction. So let's get rid of that fraction within fraction. What can I do to simplify that? Yeah, so I can sort of divide out by 1 over e to x in the bottom. Or someone said multiply by conjugate. No. But multiply by e to the x. Multiply top and bottom by e to the x, because if you multiply on the bottom by e to the x, you get rid of your fraction. So suppose you saw this, 2 e to the x, then you had e to the x, well you had 2 of them, squared plus 1 dx. Now that doesn't seem quite as intimidating. In fact, it's kind of suggestive. Because you see that e to the x dx. That says, hey, you know what? There's a good substitution you could make if you used me as your du. What would be a good substitution to make? E to the x would be a good substitution. Because if I set u equal e to the x, the du would be this e to the x dx. So this would become the integral of 2 du, because that e to the x dx is du, over u squared plus 1. Well, that's 2 arctangent of u plus a c. And u is e to the x, so that's 2 arctangent of e to the x plus c. So we can say that it's the following. Now, this is 2 arctangent of e to the x, because I just need an indefinite integral. If I know the antiderivative, then I can just substitute it from negative infinity to infinity. Now, I will say, we will be probably a little bit gentle and say, sometimes you need a limit, sometimes you don't. The times you need limits are like, what's happening to that expression? Like that log of b squared plus 1 over b, we had to think about it. But sometimes you don't need a limit because you can see what happens. Maybe we don't need a limit here because perhaps we have enough to figure out what happens. So as a reminder, arctangent has this shape. Pi halves, negative pi halves. So, as we go off towards infinity, so x is going towards infinity. Is there a question? As we head off towards infinity, what happens to this 2 arctangent e to the x? What does it do? It's going to get closer to 2 times pi over 2. Because I basically say, think about it like an onion problem. Calculus is full of onion problems because they have layers. And also because there's a couple of tiers involved. We know the x is getting big. So e to the x is getting big. So I say, okay, e to the x is getting big. So that says I'm plugging something big into arctangent. And then I say, okay, well, that's saying what's happening to arctangent as I head off to infinity. And it goes to pi over 2. All right, what happens as we go to negative infinity? What does it do? What?
The negative thing may take the e to the x to 0.
Right. So, we got to be careful here. Work your way through the onion. X is going to negative infinity. E to the negative infinity is getting close to 0. So this is getting close to arctangent of 0. So it's not going here, it's going there. And arctangent of 0 is 0. Which means another problem that's as nice as pi. All right. Find the integral of sine t over cosine t minus sine squared t minus 1 dt. All right. Well, we've been practicing this for a while. We're getting pretty good at these. What should we do? What should we do? Okay, is there a good substitution? Is there something that's saying, hey, this is what you should try substituting? Well, notice the sine t, that's attached to the dt. That's where you're going to get your clue for substitution. What, when you take the derivative, gives you something that looks like sine? Cosine. So the question is, can we make everything else in terms of cosine? Well, the good news is, we can make cosine in terms of cosine. Can we do sine squared in terms of cosine? Yeah, so sine squared, that's 1 minus cosine squared. So we could, before we make any substitution, rewrite this. We have a sine t. I'll put the dt on top. And then downstairs, okay, let's be careful here. If we replace the sine squared by 1 minus cosine squared, the minus comes through. So this would be minus minus makes a plus cosine squared. And then we have a plus cosine t. Then a minus 1 makes a minus 2. Now we follow the substitution. U equals cosine t. Du equals minus sine t, dt. So this would become the integral of minus du divided by u squared plus u minus 2. Now what do we do? Yeah, we've transformed our trigonometric problem, because this was trig, into an algebra problem, and now we use an algebra tool. So in this case, it's partial fractions. Do we need to do long division? No, because you look at the powers. Upstairs it's a constant, downstairs it's degree 2, no long division. So then the next step is factoring the denominator. Does u squared plus u minus 2 factor? I hope so, because otherwise there's not much to do. So it should factor, and I think this one does. it should factor into u plus 2 and u minus 1. And if you're not sure, just, expand out u squared. Okay, that's good. Minus u, and a plus 2u gives us a plus u, and then 2 times minus 1 gives us minus 2. So we now come to the side and do our algebra. We want minus 1 over u plus 2 times u minus 1 has to look like a over u plus 2 plus b over u minus 1. Clear our denominators. Negative 1 is equal to a times u minus 1 plus b times u plus 2. All right. Now, what do we do? All right. The suggestion is to plug in 1 because we are going to choose wisely. For a good choice will get us closer to an answer. Plugging in u equals 1, we'll get negative 1 on the left-hand side. On the right-hand side, because we made a good choice, remember we only make the good choices, like going to Iowa State. When we plug in 1, we'll get a times 0 plus b times 3. So that says that b needs to be negative 1/3. What else can we do? Negative 2. Set u equal negative 2. Well, we'll get negative 1 equals. Now, in this case, the b term drops out, and we're going to get a times minus 2 minus 1. So that's minus 3a. Or a equals 1/3. So we can now come back to our integral. So this integral is going to become a, which is 1/3 times 1 over u plus 2 plus b, which is minus 1/3 times 1 over u minus 1 du. So we integrate. Integral of u plus 2, or 1 over u plus 2. It's natural log u plus 2. Minus 1/3, integral of 1 over u minus 1 is natural log of u minus 1. Now, in this case, it wasn't a problem, but I will say that oftentimes what happens to throw people off is we might have like a u plus 1 and a 1 minus u. So if you do have a 1 minus u, don't forget to account for that minus sign. We don't have to do it there. Are we done? No. What's wrong? Yeah, we've got to get back to cosine. So 1/3 natural log of cosine of t plus 2 minus 1/3 natural log of cosine of t minus 1. And of course, we put the plus c because we want full credit. And we're done. Good. All right. Number 12. Find the integral from 0 to 1 of x times e to the square root of x. Well, what do we do? Yeah, square root of x is kind of hard to work with, so let's simplify this. So we're going to substitute u equals square root of x. If you like, that's x to the 1/2. What would du become? 1 over 2 square root of x dx. Now, we don't really have a 1 over 2 square root of x, but what we can do is we can say, oh, you know what this can be? This says that dx is 2 square root of x du, or 2u du. All right, so we can definitely make that change. So if we carry this out, let's see what we get. So we're going to get integral x, well, square root of x is u, so x would become u squared. E to the root of x would become e to the u. And then 2u du would become, dx would become 2u du. But let's be careful with the bounds, because remember, we changed this is a different integral, so you have to update the bounds. Now the original bounds, these bounds over here, these are x bounds. So you went from x equals 0 to x equals 1. But those are the old bounds. Those are not our bounds anymore, because we're switching to u bounds. So we're not going from 0 to 1. Now we're going from 0 to 1. Because Square root of 0 is 0, and the square root of 1 is 1. We did actually update the bounds, so it looks like we forgot, but no, we did it properly. We want to make sure. Sometimes they happen to be the same, sometimes they don't. Now, of course, this becomes a 2u cubed e to the u du. Now, when we see it like this, what do we know? What are we going to do? Yeah, this is a by parts problem all the way down. And so, yep. And so from here, nothing too exciting. It's just we're to be careful. And we're probably going to have to do parts multiple times. Can you actually see how many times we're going to get to do by parts? Yeah, we're actually going to go through it 3 times. But once you understand that, it's not going to be so bad. Yes?
Actually, could we cut it short by u substituting u squared, and the derivative would be 2u right now? Would that cut?
Well, but then you'd basically get us back to here. If you make the substitution.
I mean,
Yeah.
just like if you put like v equals u squared, dv would be 2
Yeah, so if you set v equal u squared, you'd return to this integral, but instead of x, you'd have v. So this is one of those, bite the bullet, you got to do it. Now, some of you may have learned some really fancy, like, ooh, I can make a table, and like, ooh, do. That's okay. We're not going to be like, you must do it by hand the long way. I do it by hand the long way because, I learned how to do calculus from the driving ed instructor. So he was not a calculus person. And so I'm not sophisticated, but that's okay. We're going to get confused because of these U's. Can we change the name? Let's call these W's. Yes. And if we have to, we can even go to triple U if the problem needs it. But I don't think it will need it. Okay. So here, there's really not much to do. So I'm just going to go through it a little bit fast. Whoops. I made a mistake right away. So the polynomial part, that's the part we're going to take derivatives of. And the exponential function is really nice. So that's going to be the part, that's the dv. Excuse me. All right. So du equals 6w squared, and v equals e to the w, meaning that we're going to get 2w cubed e to the w uv minus the integral 6w squared e to the w. And we say, all right, repeat. There's u, there's their dv, du is 12w, v is e to the w. So we get our 2w cubed e to the w minus, parenthesis, so we don't lose anything, 6w squared e to the w, then minus the integral of 12w e to the w dw. So that's 2w cubed e to the w. We still need to do this one more time. There's our u, our dv, du will be 12 dw, v will be e to the w. So let me move this down. 2w cubed. That should be w. Man, I am sorry. E to the w minus parenthesis 6w squared e to the w minus parenthesis uv 12w e to the w minus the integral of 12 e to the w dw. Okay, we're almost there. So, cleaning it up. This is 2w cubed e to the w minus 6w squared e to the w minus makes a plus 12w e to the w minus minus minus, so it's a minus. Then the integral of 12 e to the w is 12 e to the w. And of course, because we want the points, plus c. Oh my gosh, we would have lost points on this problem. Okay. We're going to do the indefinite integral. Good. Points restored. All right. Because it's a definite integral. See that? Bounds are 0 to 1. I haven't been writing the bounds down. So I want to make sure. All right. Saving the points. All right. So, are we done? No. Now we evaluate. So 2w cubed e to the w minus 6w squared e to the w plus 12w e to the w minus 12 e to the w. That's our antiderivative. Evaluate from 0 to 1. So, plug in 1. We're going to get 2e minus 6e plus 12e minus 12e. From there. Subtract, plug in 0. 0, 0, 0, negative 12. 12e's cancel. 2e minus 6e, that's negative 4e. Minus minus 12 makes plus 12. So we get 12, subtract 4e. Good. Now, is that the answer? Yeah, that's the answer. Of course it's the answer. We shouldn't doubt ourselves. The good news is 4e is a little bit less than 3, so 4e is below 12. So this is a positive number. We should get a positive value out because x, e to the square root of x is positive. So this one's not a hard one. It's just you do the work. You do the work. You might be thinking, it's the end of the test, though. What if we're mentally drained? Well, be smart. Optimize. Do the parts that you're going to get the most points on first. And then do the parts where you're going to struggle at the end. You know, get as many points as you can. You're engineers. You know how to optimize. I believe in you. All right. Find the integral of sine squared of z, cosine to the fourth z, dz. So, this is a nice trig integral. It's one of the first things we learned. How do you do a trig integral like this? Sorry, what?
You can plot one cosine.
Well, the problem is, if we pull out a cosine, we're going to get cosine cubed, and there's no nice way to write cosine cubed in terms of sine.
Power reduced sine.
In fact, we should go even further. Not just power reduce sine, power reduce all the things. All the things are getting power reduction. So that's how we're going to do this problem. So whenever you see the powers of sines and cosines are all even, it's a power reduction problem. So we have 3 formulas useful for power reduction. You're probably thinking, 3? You just said there were 2. Well, let's write them down. Sine squared is 1 minus cosine 2 theta over 2. Cosine squared is 1 plus cosine of 2 theta over 2. But then there's another one, which says sine times cosine. What can you do? It's sine of 2 theta, and then there's another 2 somewhere. Is it times 2 or divide by 2? Divide by 2. Because normally we say sine of 2 theta equals 2 sine theta cosine theta. You move the 2 across. So I actually like to use this one when I can. The reason I like to use this one is because there's less terms. You see, the cosine squared here and the sine squared, you have like a 1 plus or a 1 minus. The more terms there are, the more chances I can make a mistake. So I always like fewer terms, fewer mistakes. Well, maybe it's true. So here, bracing ourselves, preparing ourselves, we say, look, I can pull off a sine z and a cosine z. I can pick 2 off from each, and I'll be left with the cosine squared. All right. So, from the first part, sine, cosine, that's going to become sine 2z over 2 squared. Then we have the cosine of 2z. Well, let's see, what's that going to be? That is going to be 1 plus cosine 2z over 2. All right. Well, this is going to take a while, isn't it? That's okay. We're patient people. We're not in any rush. So, this is going to become the integral. We're going to have 1/8 sine squared of 2z, because I'm thinking of 2 squared times 2 is the 1/8. Sine squared of 2z times 1. And then we're going to have plus 1/8 sine squared of 2z cosine of 2z dz. Now, let's talk about the two terms. What can we do with this first one? 1/8 sine squared of 2z. Power reduction again. So, that's going to become 1/16 times 1 minus cosine, and then double 2z makes 4z. Okay, that's the first term. The second term, well, you're probably thinking, how do we do that? What's the right power reduction for the second term? The sine squared of 2z over cosine 2z. And the answer is, we should use no power reduction. We should use u substitution. This is now in a good place. This is an integral that's in our happy place. So we're going to leave this one alone. The reason it's in a happy place is because look at the powers. Sine is to an even power, but cosine is to an odd power. That's the ideal situation. When you have something, one of them is to an odd power and one of them is to an even power, then you're good to go. So now we can start talking about the integral of each piece here. The integral of 1/16, well, that's not bad. That's 1/16 times the variable, so 1/16z. Then, minus, we have the integral of 1/16 times cosine of 4z. The integral of cosine is sine. And what goes in front? Well, remember the 1/16. And then we have this 4, which is going to do a what? Which means we're going to divide by 4, which makes this a 64. Now the last part, maybe we'll do that off, a little bit of work off to the side, just so we don't make a mistake. So for this last part here, well, set u equal to the sine of 2z. Then du would be cosine of 2z times 2, which I'll bring the 2 across. So 1/2 du is cosine 2z dz. So that this would become, this integral right there would be 1/16 u squared du. So that if we integrate it, it would be 1/48 u cubed. So the last part will be, wait, did I make a mistake? Well, normally, see, if we do it here, du would be 2 cosine 2z dz. So then the 2 came across. So. No, you should challenge me. I make stupid mistakes. You're waving your hand and saying, no, Steve, you don't make stupid mistakes, but I'm assuring you, like, I make lots of mistakes. Just ask my wife. She'll assure you I make lots of mistakes. Okay, so the last part here. So this will become 1/48. U is sine, so that would become sine cubed of 2z. And of course, the plus c, because we want all those points. All right. Well, and that brings us to number 14, our final question. You are monitoring electrical generation. During an 8-hour shift, you have the following data, where you have time, and time is number of hours since the shift started, and F of t is the megawatts of energy produced at time t. So it looks like you had a pretty good morning, then maybe a little bit of a storm cloud came in, good afternoon, and then dusk, and boom, power was gone. All right. So there's 2 parts, multi-part problem. Using all of the data and the trapezoid rule, estimate the total energy produced in the shift. And part B is basically going to be the same, but instead of the trapezoid rule, we're going to use Simpson's rule. So this is all about numerical integration. We have data, and we want to estimate totals. And so you just have to remember the rules. So the trapezoid rule, it actually has sort of a nice flavor to it. What you remember is it's 1/2, and then it's the pattern 1, 2, 2, 2, 2, 1, which means the following. What you do is you take 1/2, and, I should also say, you have to, there's one other thing to keep in mind. But the question is, how much does each data point contribute? The answer is each data point is scale. So the first data point and the last data point are slightly less than the intermediate data points. They're worth half as much. The other thing to keep in mind is you need the time gap. So what's the width between our consecutive time intervals? It's 1. So there's sort of this delta t that fits in. In our case, because it's 1, it makes it a lot simpler. And so when we come down to doing the computation, so it's 1/2, and we're going to times it by our delta t on the end. We'll get to, I don't know how much space we'll need, but we'll get there in a second. So we scale the first value by 1, so that's 5, plus, then the next value by 2, next by 2, and all the rest by 2, until we get to the very last one, and that one just gets scaled by 1, and all this is times by 1 on the end. So this is our delta t. And that's actually the answer, but of course, we can probably clean this up a little bit. I mean, we might as well. So it's 1/2, 5 plus 14, plus 4, plus 8, plus 12, plus 10, plus 6, plus 4, plus 0. And we can do things, let's see, there's 10, 20. There's another 20 that makes us up to 40. And then we have 18, that's 58, plus 5 more makes 63. So this is 63 halves. Or if we were trying to look like fancy engineers, 31.5, if we like to use decimals. All right, so that's how many megawatts was estimated. Now that's not how many megawatts was produced, this is always an estimate. Whenever you're doing numerical integration, it's always about estimating the total. So that's part A. Now for part B, it's a similar process, but then what happens is it's a little bit different in the scaling. So the pattern is you scale by 1/3, but then it follows a different pattern. And the pattern is 1-4, 2, 4, 2, ... and we end with a 4 and a 1. So essentially what happens is we sort of scale, every other one gets a little bit of a boost. So that's how it works for Simpson's rule. So what do I mean by that? So in our case, it would be 1/3. We scale the first entry by a 1, so that would be a 5, plus then 4 times the next entry, which is 4 times 7, then plus 2 times the next entry, which is 2, plus 4 times the next entry, which is 4, plus 2 times the next entry, which is 6, plus 4 times the next, which is 5, plus 2 times the next, which is 3, and then we're near the end, plus 4 times the next, which is 2, and then plus 1 times 0. And again, we times it by the 1, the delta t. So it's all about proper scaling. Yes? It depends on how you view things. So there's two sort of viewpoints to have. And depending upon how you view things, then it works out. So if you view things as, so I disagree with the book. I think this is closer to what the book does. But I like to think of Simpson's rule as where you actually have sort of strips. So 0, 1, 2 is like one strip. And then what happens is you get the following thing. If you view 0, 1, 2 as a strip, what happens to your delta t? It becomes 2. So in that case, if you view it as sort of two consecutive or two consecutive pieces makes one strip, then your delta t doubles, but then this coefficient goes down by 2. So you get the same effect. And so the book says, no, don't think of it that way. The book says, just think of one time period as a strip. And now, but you treat strips as sort of like, oh, there's like a left strip and a right strip, you know. And so when you do it that way, then you get a 1/3, but then your delta t is 1. Now, you might be saying, but which one do I need to know? The answer is, whichever one you can remember. That's the one you go with. So as long as you have something that you can remember, then go with that one. Here's another check. We haven't gotten into it yet, but what should be true about these two estimates? They should be close. They may be the same, but oftentimes they're not. But they're usually not going to be like wildly different. So if your two estimates, like you do one for Simpsons and one for trapezoid, and they're like off by like double, then that means something is wrong in one of your formulas. And like, okay, let me go back and figure out which one is off. So just, that's sort of a check.
If you're using 1/3 and you're using 2 of the strips as the width, shouldn't your delta t be 2?
Well, I'm saying that the 1/3 is right if you think of your strips as sort of like time periods of consecutive hours. So the 1/3 would be the correct thing if you think of time as just small chunks. The 1/6 would be the right thing if you think of time as bigger chunks.
So what would delta t be if you have 1/6?
The delta t would be 2. So it would be 1/6 here, but it would be a 2 there, which is the same as 1/3 here and a 1 there. So at the end of the day, you actually do the exact same computation. The question is, what goes there? And they work out to balance each other out. All right, so let's actually do the computation and let's check to see if our answers are close. Because I actually don't know what this is going to turn out to be. So I'm kind of like, I wonder, I don't know. You're probably thinking, I don't know either. I don't care right now. I've been here for an hour and a half. But I'm like, ooh, I wonder if it's going to be close. Okay, 5 plus 28 plus 4 plus 16 plus 12 plus 20 plus 6 plus 8. Okay, so, all right. Let's see, what can we do? Working our way back, we get 8 plus 6, that's 14. Then 20 more makes 34. Plus 12 more, that makes 46. Plus 16, that makes 62. And plus 4 more makes 64. Then, a big number. That was a good block. 66, thank you. Plus 28, let's see, that's 86 plus 8, 94. Yeah, plus 5 more makes 99. So 1/3 times 99 makes 33. And again, to be an engineer, we'll add a bunch of zeros and say, look how precise we are. Right? So there we go. And you see, these answers are not far off. They're pretty reasonable compared to each other. And so that says, okay, we probably we're close. And if you make a small arithmetic error, okay, that's a point or 2. So don't fret about the arithmetic error. We care more about the setup. So, and that's actually it. That was the last one. Whew. Good.